Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel for everything I want to talk about science and math. And today we're in chemistry class, Unit 1, and we're going to talk about chemistry measurements. All right, see, that wasn't so awful, was it? So anyway, my production value's gone way down now. I wander off of the screen. I don't use my good camera anymore. Those took way too long to upload. Okay, also, if you're out and you want to watch the video, the school blocks YouTube. They block social media. This phone is old and broken. It doesn't have a service plan. So I can't upload it till I get home. So if you're out, you will not be able to watch the video until the evening that you were out. Okay? Everybody, did that make sense to you? Okay. All right, so here is our first unit. Chemistry measurements, where there's our standard: obtain, evaluate, and communicate information about the use of modern atomic theory. So what do you think is the study of substances and the changes they undergo? Chemistry. It is chemistry. Very good. Have I turned this on yet? Nope. Draw. Whoop, whoop. Chemistry. Good job. Okay? So there are two types of measurements. And one gives a description in a non-numeric way, and the other one has numbers. Which one do you think is which? Qualitative and quantitative. Which one do you think is non-numeric? Qualitative. Because it's like quality, right? Okay, and so quantitative, you can hear that word quantity in it, which means how many, right? Is usually numbers, and we do both in chemistry. Now, we want to be good, honest scientists and make good measurements. So good measurements are both accurate and precise. So accuracy is how close a measurement comes to the truth. That's what we would like, but a lot of times it's hard to know if we are accurate or not. So instead, we will look at our precision. Precision is how close several measurements are to, get rid of the and say each other. Or how finely stated, how many decimal points? How finely stated it is. How repeatable it is also. So how close it is to each other, how repeatable it is, how finely stated it is. Okay, are y'all okay? Am I going too fast? Everybody's written so far? Okay, y'all let me know if I go too fast with writing. Okay. So let's look at our little bullseye. Is this accurate? No, not accurate. Is it precise? Yes, because we hit the same place 3 times. So this is not accurate, is precise. Okay, how about this one? Is it accurate overall if we averaged them? No. We got 1 right, but 2 are really wrong. Is it precise? No. We're not hitting it in the same place more than once, so this is neither. Now, how about this one? Accurate and precise. Accurate and precise. And that's what we want in science. So we try to make careful measurements to be accurate. We want repeatable measurements to be precise. We want to use the best equipment we can to get the most decimal places. So that would be precise. Okay, expressing measurements. So scientific notation is a way to write really big and really small numbers. Now, why do we want to do this? One, it's easier not to have to write lots and lots of zeros. And also because of our calculators. Our calculators can do math on bigger and smaller numbers than the display can show if you just typed them in regular. Did y'all learn about scientific notation in your math classes? Some of you, yes. I used to teach it, if you look at my math classes on YouTube, I taught it in pre-algebra and algebra 1. Okay, so this is how it works. Okay, so the form is 1 non-zero digit, x, you know how in math, x can stand for a non-zero digit, and then a decimal point, then any other non-zero digits, then times, and you know how you learned, especially by 9th grade, that we don't use x for times anymore. We use a dot or a parentheses or a number sitting beside a letter in math. Well, we use an x here, okay? So for this, that means times. The big X's here mean x, the little x means x, and that's time, then the number 10, and then some exponent. So that's the form of it. Okay, we good so far? Okay, the next idea is this number, we're going to put it into scientific notation. So I'm going to wait till y'all get through writing so everybody can watch me do it. So you can do it too. Okay, y'all ready? Carson, you ready? Okay, I want to see your eyeballs, not your hair. Okay, all right, so this is how it works. There is a decimal point right here, an understood decimal point. We make the decimal point jump into its proper place. Its proper place is behind the first non-zero digit, okay? So while it hops to its place, we're going to count the hops. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this number is 1.23 times 10 to the 10th power. We feeling all right about this? Good. So let's do this one. See, that was a big number. Now we're going to do a little number. We're going to make the dot jump behind the 1. It's going to have to jump over the 1 because the dot goes after the first non-zero digit. Okay, here we go. 1, 2, 3, 4, 5, 6. So this is 1.23 times 10. Here's the tricky part. To the negative 6th. If it has a positive exponent, it's a big number. If it's got a negative exponent, it's a little number. We're going to write that down on the next page. So if you turn the page over, a big number is a positive exponent, a small number is a negative exponent. See how fast we can go? Am I filling the blank ways? Yes, Mr. Carson.
Why is it 1.23 not?
Why is that 1.23 what?
Why is it 1.23 not 12.3?
Because there is a little bit of etiquette to science. And the etiquette of this is that you put just one number, then the decimal point, then the rest of it. One digit, then the rest of it. So that would just be not proper for it to be 12.3. There's an etiquette to it. And as we get into it a little bit further, you'll understand why a little bit more. There's a reason behind the etiquette. It has to do with something else we're going to learn today called significant figures. All right, we feeling good about this so far? Okay, so now get out your calculator. Take a look at it. Okay, so one of the reasons why we do this is so that we can, where did I put my calculator? So that we can, oh, there it is. So that we can tell our calculators these numbers. And, okay, so, and you're always going to want, if it's a number like this, to use this method. You don't want to put 1.23 times 10 to an exponent. It'll give you the wrong answer. The reason why it gives you the wrong answer is because you remember when you learned terms in algebra? X squared's a term, 3x is another term. Remember the terms part of algebra? Y'all do remember that? Okay. If you do that, this is one number, and your calculator will think it's 2, and it will do the math on it wrong, and it will give you the wrong answer. So everybody's got to commit to doing it the way I'm going to teach you right now. All right. So in this way of shorthand of telling our calculators, a capital E means times 10. So we're going to, first of all, I'm going to put this number in scientific notation, and then we're all going to practice putting it in our calculator. Okay, so my Decimals right here. 1, 2, 3, 4 hops. So this is 3.6 times 10 to the 4th power. Now, everybody look at your calculator. You're going to have a button that says EE or EXP or SCI or times 10. The EE might be painted above a button and not actually on the button. On this calculator, it's right here. It's painted behind the painted behind the comma. Okay. On this calculator, if you have a Casio, it says times 10 to the X at the bottom. That's your button right there if you got a Casio. If you've got this one, it's right there at the end of my finger. It's a button that says EE. Do you see it? Okay, if you have, let me find one of these. I have one, y'all might have taken them off. I wanted to show you the 36. I don't have a 36. Let me see somebody who's got a 36. Oh, thank you, man. Okay, if you've got the 36, it is a button right there at the end of my finger that says EE. You see that? Okay, has everybody found your button? Okay, well, we're going to together put this number in our calculator. This is how we do it. You start by putting 3.6. The point is at the bottom usually, 3.6. Now you push your button, and the button means times 10. So we don't hit times and we don't hit 10. We're going to do EE. For me, it's second, comma. To get to the painted on part, you have to push second. And on my calculator, it puts a capital E. Do y'all see that? That E means times 10. And now I don't go up into exponent land. I stay in numerator land, and I put 4. Okay? Now you can hit enter and see what it does. 3.6 E4, enter. Sometimes it will take it back out again. Did it take it back out again for you? What did it do when you hit enter? It gave you the original number or that number again? Some other times it will give you the original number. Okay, so now let's do this one. This one is 1, 2. So this is 2 times 10 to the 2nd. Now I want you to put both of these numbers into your calculator, multiplying them. Do 3.6 times 10 to the 4th, which will be 3.6 E4 times 2E2, and see what you get for the answer. Multiply these two numbers together. So I'm going to put mine in again, 3.6 EE4 times 2 EE2. So what'd you get for your answer? You got it? What is it, Mark?
7,200,000.
Okay, can you say that to me in scientific notation?
7.2 times 10 to the 6.
Okay, 7.2 times 10 to the 6, or your calculator might have said 7 to 1, 2, 3, 4, 5. Did everybody get one of those two? Yay! Okay. All right. So now we're going to try the next some small numbers. Okay. So this one, try to put that one into scientific notation by yourself, just writing it. See if you can do the frog hopping by yourself, and if you can put that in scientific notation. See if you can do it. Okay, if you can't, you can watch me. 1, 2, 3, 4, 5, 6, 7. 3.3 times 10 to the negative 7th. 1, 2, 3. 4 times 10 to the negative 3rd. I want you to divide them and see what you get. See if you can divide those two numbers and see what you get. 3.3 E negative 7 divided by 4E negative 3. Give it a try. You should get 8.25 times 10 to the negative fifth, or 0.40825. Everybody getting it? No. Okay, so let me see you put it in. Once again, my good production, wandering out of the shot. Okay. Okay, so this number, let's look at this one. Okay, so we're going to do 3.6, and then your EE is right there. So you do second, that button, that means times 10 to the fourth power. Now we're going to say times, and we're going to do this number, 2 EE 2. And we say enter, and there it is, 7, 2. Okay, and if we put this in scientific notation, it'd be 1, 2, 3, 4, 5, 6, 7.2 times 10 to the 6. Okay, anybody else having problems getting in your calculator? Okay, we got a few more here. Okay. Okay, I know what you're doing. I think that is not negative. You pushed this, didn't you? That's minus, that's negative. Excellent. Let me explain to you. You got to push this one for the negative. That one's minus, that's negative. Let me tell y'all what he was doing wrong, because I should have taught it to you and I forgot. Okay, so everybody look at your calculator. There are two things that look like minus buttons. There's one over on the side, and that means subtract. There should also be one probably in parentheses at the bottom, and it might have a plus and a minus with little arrows between them. That is negative. You've got to push the negative, not the minus, or else it will give you error. Okay? Somebody else, you were not getting it? Okay. We'll do a couple more and then we'll move on. Let me see what you're getting. Okay? Your calculator's not doing anything, it's dead. Let's see what we got. We got batteries in it. They're not corroded. Sometimes if you turn them on, okay, you're gonna just have to wait till you get batteries. Okay. Who else? Okay, so yours, the button. No. Did you get this from me or is this from yours? Yeah, because I've had people that they're all right. I need to look at your calculator a little bit more. I think it is okay. I think it's like in my head that it's okay. I just gotta think. It's got some probability of, oh, it's this. See that times 10 in, you got the times 10 button like a Casio. Okay. Anybody else? All right, good job. Next idea. Okay, so we want to be honest scientists, and we don't want to make it look like our lab equipment is better than it is. So if I said that I had measured something to 0.000000429, that's saying I have some really expensive equipment that can measure that finely. So when we do math on numbers, on our data, we need to know where to round for us not to make it look like our equipment is better than it is. Did you follow that? So you ever been in math class and you thought, well, how far should I round? Do you ever ask your teacher that? Well, in science, we have rules. You don't have to ask your teacher. The rules tell you how far to round, okay? And it is something called significant figures or significant digits. Now, we are a little bit nerdy in science. I don't know if you've ever heard that before, but it's true. And so we like to say things in little cool terms. And so sometimes we'll call it sig figs or sig digs. Doesn't that sound much cooler than significant figures? Sig digs. Sounds very cool. Okay, so the question is, how do you round? Well, first of all, how you round in general is 5 and up, round up. Now there is a curriculum, and you only look at the digit next to what you're rounding to decide. There is a curriculum that is used in private schools and some home schools that teach this wrong. They have you look at the very beginning to round, go all the way over. You don't. You only look at the number next to where you're rounding to. So if you're rounding to the tens, you only look at the ones. If you're rounding to the tenths, you only look at the hundredths. Are you following what I'm saying? Okay, you only look at the digit next to it. Now why? Why do we do this? Because we want to be honest scientists and not make our data look better than it is. Okay? So, but first of all, you do your math using all the digits you have. You do not round to the very end. Don't start rounding in the middle. It'll give you the wrong answer. Okay? Was that too fast? Do I gotta scroll back?
You scroll back up.
Okay, yep, I understand. We can wait a second, and this is my chance to drink a little water. And look at the time, see how I'm doing. I'm doing fine. I left my watch at home today. I put a hair tie on my wrist, and I guess it felt like a watch. And I didn't think to put on my watch. It's been very annoying. Okay, we good now? May I scroll? Okay. All right. So there are different rules for adding and subtracting and multiplying and dividing. So first of all, the rules for adding and subtracting, you round your answer to the same number of decimal places, that should say as, not and, mark that out and write as, the number with the least number of decimal places. So what that means, if you're adding and subtracting, and you have one number that goes to the ones, and another number that goes to the hundredths, you have to round to the ones. Whichever one's the worst, that's what you have to go with. Does that kind of make sense? Well, we'll do some problems. It'll make more sense. Okay, now multiplying and dividing is more complicated. There are rules we follow, and these are the rules, okay? You round your answer so that your answer has the same number of significant figures as your number with the least number of significant figures. Now, I know that sounded like gobbledygook, but let me show you how it works, and it'll start making more sense. Okay, these are the rules of how you determine how many significant figures are in a number. And then once you figure out all your numbers who has the least number of significant figures, you round your answer to that number of significant figures. Don't worry if that didn't make sense. Okay, all non-zero digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, are significant. So 1, 2, 3, 0.45 has 5 significant figures. If it's not a zero, it counts. So the thing that's really what you have to figure out is, does a zero count or not? And it depends. The next rule says zeros that are between not zeros are significant. So see how that 0 is between 1 and 2, and 1 and 2 are not zeros? That means zeros in the middle count. That 0 counts as being measured or significant. So it has 3 significant figures. Isn't that fun? You're getting to learn something new. School is very boring to you honors kids a lot of times because you learn the same thing over and over again. It's never challenging. See, you're not bored. You're learning something new. Okay, the next one. Zeros that start a number, zeros at the beginning, are not significant. They're considered placeholders. So 0.002 only has 1 significant figure. Those zeros at the beginning don't count. Okay, next idea. Zeros at the end of a number after a decimal point count. So 21.3000 has 6. 1, 2, 3, 4 has 6. Zeros at the end after a decimal count. Zeros at the beginning don't count. Zeros in the middle count. Okay? Last one. Zeros at the end of a number with no decimal do not count. So 4,200, zeros at the end, no decimal, has two significant figures. Don't worry, once you practice it, it will be easy. And it's what I gave you your worksheet on today to start practicing, the worksheet I gave you. All right, are we good to move on? Okay, next idea, changing between measurements. Okay, we're going to learn two different ways to change between measurements. The first one is called factor label or dimensional analysis. Okay, and how it works mathematically is using conversion factors. Conversion factors mathematically equal 1. If you have the same thing in the numerator and denominator of a fraction, it equals 1. 3 over 3 equals 1. A billion over a billion equals 1, right? If you multiply anything by 1, it is itself. 7 times 1 is 7. A billion times 1 is a billion, right? Yes? So what you do is you use conversion factors, things that are equal to each other, things that are mathematically equal to 1, to change units about things. Now, I'll show you, it'll make sense. All right, so for example, a conversion factor equals 1. I'm going to write O-N-E so you know it's not length. For example, 1 meter equals 100 centimeters. 7 days equals a week. 12 inches equal a foot. These are things that are equal to each other. So if I wrote them as a fraction, they would be equal to 1. Now, if that does not make sense to you, it doesn't matter. You don't have to understand why to be able to do this. Just some students over my decades of teaching, and we're not going to talk about how many, I have found some students, especially honors, learn better if they understand why. And if you don't tell them why, they can't learn it. My son Josh, the youngest of my 3 boys, is like that. He could not learn chemistry until I sat down and explained to him the periodic table and the thing called periodicity. And once he learned that, then he could go and learn the rest of it. But he couldn't learn it when he wasn't understanding why. Well, why does the element want that? Okay, so this is our little thing here. How many seconds till break? Now, we're going to assume we're not going to have a snow day. So our break is going to be, let's see, it's going to be right here where Wednesday, 1, 2, 3, 4, 5, 6, 7, 8. We'll say 8 days till break, okay? So I don't know how many seconds till break, but I'm going to say there's 8 days. And we're going to convert 8 days to seconds so we know how long it is to our DLD. Okay, whenever you do one of these problems, first you're given a number, you start with that. And I call that starting with what you know. Now, when I call on you, sometimes you guys will just look at me like a deer in the headlights and go completely blank. So I like to give you a little hand signal to kind of jump start your memory so you know what to do. So when we start a problem, I'll ask you, what do we start with? And I do this, and I'll say, what do we start with? And it is what we, and you say no. Okay, so we always start with our given, but we're going to call it what we know. Okay, so let's practice your part. What do we start with? We start with what we know. That was pretty weak. Let's try it again. We start with what we know. Much better. Okay, so what we know is 8 days. We start with what we know. Now, you could write parentheses and fraction bars and time signals, but I've been doing this long enough that I have learned that a better way to do that is to use what they call railroad tracks. They don't really look like railroad tracks. They look more like braces on someone's teeth. But that's what it's called. I didn't name them. Okay, and the reason why is when people use parentheses, I've seen students have such messy handwriting that their parentheses turn into sixes, and suddenly they've introduced a six that doesn't belong, and they get the wrong answer. And people don't do it with the railroad tracks. So first we write 8 days, and now we put our railroad tracks. On top of the railroad tracks equal the numerator, the bottom is the denominator. Then we take the units that we have in the numerator and we push them down to this square in the denominator. It's more fun if you add sound effects. You can do math without sound effects, it's just not as much fun. So I pushed it down to days. Now, I don't know how many seconds are in a day. So I'm going to have to break it down some more. But I do know how many hours are in a day, and I can write here what is equivalent. There are 24 hours in one day. This is a conversion factor. 24 hours and one day is the same thing. This is mathematically equal to the number 1. Everybody good so far? Now, why would I want to do that? Because I want to change units. And in math, if I have the same thing in the numerator and denominator, I get to do one of my favorite things in math. I get to cancel them out. I like canceling out. I know it's just psychological, but it makes me feel like I'm boss of the math. I get to cancel you out. Math, you're not the boss of me. I'm the boss of you. I'm marking this out. Okay? So hours are not what I need, so I got to keep going. I take the hours and I push them to the denominator. And I put hours down here. Nope, still don't know how many seconds are in an hour. But I do know how many minutes are in an hour. What's the relationship between minutes and hours? 60. 60 minutes in 1 hour. Now I'm getting somewhere. Hours cancel out. And now minutes go to the denominator. I push them over there. More fun with sound effects. And now I know the relationship between minutes and seconds. There's 60 seconds in 1 minute. Minutes cancel out, and I got what I was looking for, seconds. Numbers on top get multiplied. Numbers on bottom are divided. So on your calculator, do 8 times 24 times 60 times 60, enter, and somebody tell me the answer. I don't want to have to do it. Y'all do it. Tell me the answer. What is it? 8 times 24 times 60 times 60.
691,200.
691.
And then comma 200. 2 zeros.
And then 2 zeros or 3 zeros?
2
No.
0 0.
2 0 0. So we have 691,200 seconds, give or take a few, right? Till we are on our DLD before MLK weekend, where we get MLK Day off. Okay, so here's another example. How many centimeters in 4 feet? So what do we start with? Oh, that was even worse. What we know. So what we know is 4 feet. I push feet to the denominator. I don't know the relationship between feet and centimeters, but I know that the relationship between feet and inches. How many inches are in a foot? 12. Did you learn the rhyme when you were in elementary school? Did y'all learn this? Stop, kaput, 12 inches in a foot. It's a little first grade thing. Oh well, now you know it. Stop, kaput. Okay, feet mark out, inches go to the denominator. And I do know the relationship between centimeters and inches. There's 2.54 centimeters in 1 inch. So inches mark out, and now we can do it. 4 times 12 times 2.54. You don't have to do the ones. Anything added, multiplied, or divided by 1 is that thing. So this one is 121.92 centimeters. When you finish a problem in this class, always put a box around it. I used to teach in Cobb County with bad kids, and they would cheat by not boxing their answer. I'm sure this would never occur to good Paulding County kids. But bad Cobb County kids, they would do a problem every possible way. They would take the numbers and add them, subtract them, multiply them, and divide them. Hey, they might even do the square root on it. They're just going to try every button on their calculator on those numbers. And then they'd turn in their test and say, and I'd mark it wrong, and they'd say, no, but see, the right answer was here. But I'm like, but you got 10 other answers here too, and you got to pick one and put a box around it. See, that never occurred to y'all, did it? To try to do a problem every way possible. I tell you, those bad Cobb County kids. All right, I loved it though. I cried when I left Cobb County. I was so sad. I was like, I'm not sure I want to give up teaching in public school. And see, I didn't end up giving it up. I came back. Okay, and how are we feeling about this? This is called dimensional analysis. We will be doing this for the rest of this class. This is a concept that doesn't go away. So you need to get good at it. Okay, next idea, international measurements. Okay, in science class, we use measurements that can be understood all over the world. My son Nathan will sit there and watch videos from India and China with people doing chemistry. He does not speak those languages, but he can watch them, what they're writing on the board, and he understands the math, and he understands the periodic table, and he can understand those videos without understanding a word they're saying. So that's pretty amazing to me. I've never done that because he's at a higher level than me. He is going to have a doctorate of chemistry. I was just a biochem major. So I am not anywhere on that level watching people in India doing chemistry, but he does, and he can understand it. So that's pretty cool. So the system we use that people can use, understand all over the world is called, and I'm sure I'm saying this in perfect French, Le Système International des Units. But we don't really say it in French. We call it SI. So, or we'll also call it the metric system. The metric system is slightly different than SI, and sometimes we use metric and sometimes we use SI. So how this measurement works is there are base units that we add prefixes to change what they stand for. So for example, in SI, in the metric system, the base unit of length is the meter, and it is abbreviated lowercase m. Now, y'all have probably learned this before, right? This is a review, right? Y'all have heard of the metric system before, yes? Nod to me. Tell me yes, you've heard of this. Okay, good. So, see, there's my little French stuff. Okay, so mass is the gram. It's lowercase g. Time is the same as it is in English. It's second, lowercase s. Current is amperes. It's capital A, but usually we don't call them amperes, we call them amps. You ever heard of amps with your stereo or something? Temperature is Kelvin in SI, and we're going to use that later when we learn about the gas laws. It's a capital K, and in metric it's Celsius. Have you heard of Celsius degrees? And that's a capital C. Now, we also, here in the United States, we also use English measurements like Fahrenheit, yards, pounds, but in science class, we're going to use the metric system. Now, I think they should make me queen of math and science, and when we do, we're not going to use two systems anymore. Well, we will, but I'll be in control of it. We'll use English every day, miles, pounds, feet, and then we'll use metric just for science. English, I think, is a better unit for everyday use, and metric is better for science. Yes, ma'am. Talk louder. What?
What does the third one say?
The third one, it is amperes, A-M-P-E-R-E-S, better known as amps. Okay. Okay, volume is liters, capital L, or it could be a cubic length, like cubic centimeters, and 1 cubic centimeter equals a milliliter. So in medicine, they'll use cubic centimeters or cc. You'll hear that on TV. Quick, give him 100 cc's of epinephrine, quick, in his heart. And somebody's dead, and they'll put 100 cc's of epinephrine in their heart and wake them up. They come back to life. Okay. So in medicine, they'll use cc, standing for cubic centimeter, and in science, we usually use milliliters. Okay, but on the test, this is a question. You have to know that 1 cubic centimeter is equal to 1 milliliter. Okay. Energy is measured in joules. It's spelled different than like diamonds or rubies. It's a capital J. Pressure has a lot of units, and we're just going to learn a couple of them here, and we'll later watch a video, a very exciting video, about why. So one unit is called atmospheres. Another one you hear sometimes is millimeters of mercury, which is mmHg. Another one you might hear of, like on the weather, is bar. So those are some pressure units. Okay, so one reason why the metric system is so good for science is it's easier to do unit conversions. So you don't have to always do dimensional analysis or factor label to change between units. And so there's another method that I call the frog jump method, and it's based on this acronym, sort of acronym. King Henry's daughter bakes delicious chocolate muffins. So the King Henry's daughter is a princess, and in particular, she's Princess Tiana. So I put a Tiana on y'all's notes, and she didn't come out good. Can you tell it's Tiana? That's Tiana. It's got to be Tiana. Why does it have to be Tiana? Because not only do we have a princess, we're going to have a frog, and she is my favorite Disney princess. She's a Southerner. She's got a good work ethic. She's in New Orleans, a very cool city, so we have to have Tiana. Okay, all right, so this is the frog hop method. You have it, so this is what King Henry's daughter bakes delicious muffins stand for. KHD, King Henry's daughter bakes delicious chocolate muffins. Everybody see that? K stands for kilo. I think I'm going to write it over here. Big D stands for deca. I left off Henry. Well, let me do this right. Erase that. I got out of order. I got too excited about the deca. Okay. Big H is hecto. Big D is deca. Okay. B stands for basic. Little d is deci. C is centi. And M is milli. And those are the prefixes that we can use to convert between units. Okay, so this is how you do it. Prince Naveen is our frog, and he is our decimal point. And he is going to hop from one to the other, and that's how we're going to switch, the frog hopping method. Okay, we're going to change 4,800 kilometers to millimeters. Everybody ready? Watch me do it. Okay, so what I do is right now, Naveen is right here in his little decimal place after the 00. Let's see if I can make it bigger so y'all can see it better. Okay, and he is going, he's right there, and he's starting at kilo, and he's going to jump to milli. Everybody see what we're doing? And we're going to count the hops. 1, 2, 3, 4, 5, 6. Everybody see how Naveen hopped 6 places? Okay, so now he's going to hop from here. So he's at 4,800. He's going to hop from where he is right now, the same number of hops and in the same direction. 1, 2, 3, 4, 5, 6. Now we have hop places, and we fill those places in with zeros. We augment zeros. Remember learning that when you learn long division? So the answer is this number, MM. Isn't that easier than those train tracks? That's why see my crown over there? I always tell kids I want to be queen of math and science, so I'm going to make some changes. And so over the years, I've had kids say they agree that I should be queen and have given me things like crowns. So I'm very opinionated about things. Okay, so now we're going to go from 6 liters to centiliters. So basic is your basic unit. Yeah, it's meters, it's grams, it's liters, it's amperes, it's Fahrenheit degrees, whatever it is, not Fahrenheit, Celsius. And so this is basic. Liters is basic. Everybody understand that? This is something people get mixed up on. Okay, so now I'm going to change the color. We're going to go green this time. So this time I'm going from basic to centi. So I'm starting right here, and I go 1, 2 hops. Everybody see how I did that? So now I'm on 6. Naveen is right here. We're going to go 2 hops this way, and it's going to be 600 centiliters. Okay? Do you want to try one by yourself? You want to try the next one? Try the next one by yourself, and then I'll do it. I'm going to change my color again. I'm going to change to purple. So, no, I think I'll do blue. I'm ready to do it. This time I'm starting at milli, and I'm going to big D deca. 1, 2, 3, 4, this way. So I start right here, 1, 2, 3, 4. So the answer is 67.9 big D G, decagrams. Do you like this? See ya, no, I do not like this. You might need to watch Princess and the Frog so you can just love this a little bit more, because it is so good. Okay, next idea. And we're gonna do it quick because we're almost done. See what we got here. Yep. Okay, so we need some math to do to practice these ideas. So density is a good one. Density is equal to mass over volume. It's how heavy something is for its size. So how we do these problems is first of all, I want you to annotate your problem. So what is the density? So I know density is what I'm looking for. So I put a question mark over it because that's what I'm looking for. A piece of lead. Lead is a chemical that might be important, so I circle it because this is chemistry class. That has a mass, so 114 grams is a mass, and a volume of 10 milliliters. Next, I list my knowns and unknowns. So density is what I don't know. The mass is equal to 114 grams, and the volume equals 10 milliliters. Next, I think, is there a formula I know that relates my knowns and unknowns? And there is. It is density equals mass divided by volume. I write my formula every time. It's showing my work, and showing your work's important. That's showing your teacher that you didn't just do a little sneak peek on someone else's paper, that you actually know how to do the problem. Next, for the unknown, you leave it a letter. But for the knowns, you substitute them in. Now, I like to sing a song here. It's from before my time, so I know it's before your time too. It's Substitute by The Who. So you sing substitute. Now, you can do math and science without singing and dancing, but you're not having all the fun you could. You need sound effects, dancing, singing. I promise it helps. Okay, so the mass is 114, and the volume is 10, and I can do this math in my head. It's 11.4 grams per milliliter. Put a box around it. So that's how we're going to do problems in here. Told you that'd be quick. Okay, you ready for one more idea? One more idea. Last idea for this unit. I'm going to wait till y'all look like you're through writing. Okay? The last idea is moles. Have you noticed I have all these cute little stuffed animals around my room? Can you see them in the video? Yes, you can. This one is supposed to be me. Looks just like me, right? Okay, anyway. So, why do I have moles around my room? Do I love moles? Not particularly, but it's a science thing, okay? So, measuring in moles. When you buy eggs, what unit do you buy eggs in? This isn't tricky. Go to the store and buy a dozen eggs, right? And so dozen is a word that means a number. What number does it mean? 12. What do you buy socks in? Do you buy one sock? No, you buy them in pairs, right? So pair is also a word that means a number. What number does it mean? 2. Now, 2 actually has another name, couple. So 2 has 3 names. It could be called 2. It can be called a pair. It can be called a couple. All of that means 2, right? Well, in chemistry, we don't use dozens and we don't use pairs. We use another number called a mole. And it has nothing to do with the cute little animal, except we chemistry teachers like them because they're cute. I have a whole periodic table of moles back there. There's a mole over there on the box. There's moles here, there, and everywhere. Okay, So just like the mole, just like pear, this number has three names. It can be called the mole. It can be called Avogadro's number, after the guy who invented it, Amadeo Avogadro, and he really looked kind of like that. He was an unusual looking fella. Or it is this number, 6.02 times 10 to the 23rd power. So we use this like to convert. It is what I use to measure out chemicals to make things in lab. That's what it's used for. So 1 mole of a chemical is its mass in grams. That is called molar mass, or abbreviated M&M. And you get it off of the periodic table. So everybody look at the periodic table. Do you see how I have M&Ms next to the word table? Everybody see that? That is to remind you that if you need a molar mass, where do you look? The periodic table. Do you see the numbers written in red underneath the letters that are a decimal? That is the molar mass of the different elements. So, somebody who's close over there, can you see what the number is underneath number 7, nitrogen? Do you see number 7, the blue number 7? What number? What's the red number underneath it?
14.0067.
So it's a big number, 14.0067. For right now, we're going to round them off to a whole number. So nitrogen is 14. What would lithium round off to? It's 6.9. So what should we round it to? 7. Oxygen is 15.99. So what are we going to write? 16. Hydrogen is 1.001. So what are we going to round it to? 1. How about water? Is water on the periodic table? No. What's the formula for water? Look at all the chemistry you already know. Look at y'all. So for water, I need to add up 2 hydrogens and 1 oxygen. 16 plus 1 plus 1 is equal to 18. So that's how you calculate the molar mass. You look up those numbers and you add them up for how many you got. Okay. So how you do the mole problems. Once again, you're going to write what you know. You're going to write the units of what you know in the denominator. You're going to think of a conversion factor and do the math. So let me show you what I mean by this. How many grams, so I'm going to put a question mark over grams, are in 4 moles of carbon? I'm going to start with what I know, which is 4 moles of carbon. Now, a mole has an abbreviation. And this is one of the nerdiest things about chemistry. The abbreviation for mole, M-O-L-E, is M-O-L. Woo, get to rest your hand and not write that E. Okay? We draw our train tracks. What's going to go into the denominator? Mole, right. And now we think about the conversion factor. And what we want to change it to is grams. What this is, that number 12 on the periodic table under carbon is 12 grams per mole. That red number, the unit of it is grams per mole. Moles cancel out. I multiply anything on top, I divide anything on bottom. 4 times 12 is what? Do you know your 12s? It started with a 0, 12, 24, 36. 48, 60, 72, 84. I tell you, if you're not singing your way through math, you're not having fun. So it's 48 grams per mole. Put a box around it, and that is unit 1. Ta-da! Science is great.